of problems that I think are pretty good and portable among, wherever you're taking organic chemistry 1. If you're in organic chemistry 1 and your exam 1 is fast approaching, I think the problems I've picked for today, I think they're going to apply to your class. So what I want to do over the next hour or so, hopefully not super duper long, is to go over these problems that kind of start out in the Gen Chem world in terms of, Lewis dot structures, resonance, hybridization, formal charge, then kind of moving into like acid base world, and then going from there into, naming, and then all different types of alkane topics from free radical halogenation to cycloalkane stability, Hammond's postulate, and then and Newman projections. Okay, so without further ado, let me just check one more thing. And thank you, McKenna. Hail to Pitt. You rock. All right, cool. We'll just dive right in. So I won't really have eyes on the chat. I'm just going to kind of be focusing up on here. But Vinayak, who is part of the JoChem team, I believe is in the chat. If you have any questions in general, I think he's around. If he is, that's great. If not, I know he's a busy guy. So, all right. So in terms of the first problem I want to do, let's start off with a Lewis dot structure problem. So if you don't have, I totally imagine you're going to have to draw a Lewis dot structure on your first exam. And sometimes it's one of those things where you think you're totally solid. I know I had this type of issue come up for me where I kind of missed easy points. So what I want to do in this first problem is we will draw the Lewis structure for acetonitrile oxide, which the chemical formula, which is, we don't really know what this is, but you would be given something along the lines of this. So part, A of question number 1 will be draw a Lewis structure. How about that? Draw a Lewis structure. And then one thing we can, well, actually, hold on, I'm going to kind of amend that. Sorry about that. It's been a while since I've done these. Draw all, say this. What I meant to say was draw all resonance forms, which is really saying, draw a Lewis dot structure, and then from there, draw the various resonance structures that can exist for acetonitrile oxide. So we need to draw a first Lewis structure before we can kind of come up with the other resonance forms. So remember, the foolproof way of doing Lewis dot structures, I know you might be better or more advanced, but the total way to do it, if you forget everything about drawing Lewis dot structures, is to first come up with your electron total. So if we look at this over here, we know we get 3 electrons from hydrogen, 3 hydrogens. So we can kind of do 3 from 3 H's. We have 2 carbons, so we get 4 from each. So because we have 2 carbons, that means we'll have 8 from carbon. We have 1 nitrogen. Nitrogen comes from the 5th column of the periodic table, so it brings 5 electrons, valence electrons to the table. And then we have an oxygen, and that brings 6 because oxygen is from the 6th column of the periodic table. All right, so tally that up. We have 11, 16, 22 electrons total to work with, okay? And then we can jump into drawing the Lewis structure, or a first Lewis structure. Now you can kind of assume the skeleton is gonna look right along like this. So the kind of backbone will kind of look like that. And then as you can probably assume, this carbon will be attached to these 3 hydrogens right here. So I'll fill those in. I'm going to connect everyone together. And the goal, what I'm first going to do, and I'm probably going to overshoot my total, is just give everyone a full octet. So I know this is not what will look like at the end, and it's kind of absurd to give carbon that many lone pairs, but this at least aims to give everyone a full octet. And then now what I'm going to do is count up the electrons I have here, compare against here, and see how much I've overshot, and then we can consolidate by taking lone pairs and making double or triple bonds. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Actually, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay. That's 4 too many. So I need to chop down my total count by 4 electrons, and I can do that by, what I'll first do is, and again, you can choose wherever, but I'm gonna go here. I'm gonna take a lone pair away from each carbon and nitrogen and make a double bond. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, I'm getting closer, but I need to do this one more time. What I can try is now make a double bond between nitrogen and oxygen. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Oh wait, 2, 4, 6, 8. Oh, whoops. Hold on. Actually, I'm going to undo what I just did there. I'm actually going to do this. Okay? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Now this is a valid Lewis structure. Cool. What we can do from here now is, well, we need, before we kind of like give it the full thumbs up, we need to make sure if there are any formal charges, we need to assign those. We see that the structure is neutral overall. So I know from carbon here, 1, 2, 3, 4, carbon comes from the 4th column of the periodic table. It's in control of 1, 2, 3, 4 electrons because we split electrons, split bonds that atoms are involved with when we're assigning formal charge. This carbon over here is in control of 1, 2, 3, 4. This nitrogen is in control of 1, 2, 3, 4. Now nitrogen comes in with 5 valence electrons, but it's in control of 4. So this nitrogen is actually a +1 formal charge. Now for the oxygen, we see it's actually in control of 1, 2, 3, 4, 5, 6, 7. It's in control of 6. Sorry, it comes in with 6. It's in control of 7. It has a -1 overall. So we've actually assigned all the formal charges here, and they make sense because the molecule overall is neutral. And even though there exist charges within the molecule, it's neutral, okay? So long way of getting to a first structure. But now what we need to do is actually draw all the resonance forms. So what we can do from here is draw a double-headed arrow like so to say, hey, look at me. I'm gonna draw some resonance. And a valid resonance move I can do here is I know I have double bond, I have bonds to work with over here, and I have a lot of lone pairs here. So what I can draw is a double-headed arrow because I'm going to move 2 electrons, and I'll show this lone pair swinging down and forming a double bond between nitrogen and oxygen. Now, if I do nothing, nitrogen will have 5 bonds, and that's a big no-no. So what I can do is, because I'm kind of moving electrons in this direction, I can kind of offload a pair of electrons between nitrogen and carbon onto carbon. So what I can do is have this now. I didn't touch anything on the end of this structure. I now have carbon with a double bond and a lone pair. I now have nitrogen over here with a double bond on both sides. And I just have oxygen with a double bond and 2 lone pairs. It doesn't matter that we moved this one on the bottom. As long as you just have the correct number of lone pairs after you move them, it's totally fine where they are. Now, I shifted things around, so I have to redo my formal charges. If I look here now, oxygen is in control of 1, 2, 3, 4, 5, 6 electrons. So 6 minus 6 is 0. Oxygen's neutral. If you can see, nitrogen's actually in the same position as it was above. 1, 2, 3, 4. 5 minus 4, plus 1. So nitrogen has a +1 formal charge. Didn't really change. But carbon, on the other hand, 1, 2, 3, 4, 5. Carbon comes in with 4 valence, but now it's in control of 5. So carbon actually has a -1 formal charge. So you can see we actually have a kind of a different charge setup than we did above. And we've drawn 2 resonance forms. We can actually draw 1 more. I'm going to go over here. I can actually do the same maneuver 1 more time. I can have oxygen share a little bit more. And to avoid breaking the octet rule with nitrogen, I can bounce yet another pair of electrons onto carbon. So that looks like this. Carbon has 2 lone pairs now because this double bond kicked up to be another lone pair. Nitrogen has a single bond on the left-hand side, but now it has a triple bond on the right-hand side with oxygen, and oxygen only has 1 lone pair. Again, this is now a valid resonance move. We've shown our arrows over here. We've drawn the double-headed arrow, but now I need to assign formal charges. Carbon over here has 1, 2, 3, 4, 5, 6 electrons that it's in control of. So it comes in with 4 valence. It's in control of 6. So it has a -2 formal charge. And trust me, we know that's not great. Nitrogen hasn't really changed. It kind of looks like it did at the very beginning. 1, 2, 3, 4 comes in with 5, is in control of 4. 5 minus 4 is +1. And oxygen is in control of 1, 2, 3, 4, 5. 6 minus 5, it has a +1. Okay, so we've completed the bear that was part A. We've drawn all the resonance, we've drawn a valid Lewis structure and all the resonance forms of acetonitrile oxide. Now, the slight follow-up to this is identify the major and minor contributors to the overall resonance hybrid. Now, remember the rules that we have in terms of, evaluating the stability or like the quality of a resonance hybrid. Because remember, we don't always just look like this, or this. We're a constant mixture of all three. These electrons that we're showing moving, they're constantly moving. They're very dynamic. We always want to have full octets. And as we can see here, every structure we've drawn is valid and has full octets. Now, the second thing we want to try to maximize is placing charges on atoms that like them. So, avoiding, giving negative charges to electronegative atoms, and then putting positive charges, if we have them, on atoms that aren't very electronegative. And then the final thing is to avoid, if possible, putting like charges next door to one another. So if we take a look here, I hope we can all agree this is a dumpster fire. This is garbage. Garbage for a few reasons. One, we have a double negative charge on an atom that is not even electronegative at all. So that's really, really, really bad. That makes us extremely, extremely sad. And on top of that, we have neighboring atoms having plus charges. So this is like a double whammy of awfulness. If we look over here, we're certainly better than the one we just took a gander at, but we're still not great, right? We have a negative charge in the structure, but it's on an atom that isn't electronegative. Nitrogen is more electronegative than carbon, and oxygen is even more electronegative than nitrogen. So this is better than the one we just came from, but this is still kind of problematic. Now, ironically, if you look at the first structure that we drew, we see that we have an oxygen with a negative charge, and we like that. That's so much better than having a negative charge on carbon, and certainly better than having a 2 times negative charge on carbon. Additionally, we have a positive charge on nitrogen, but hear me out here. We have a positive charge on nitrogen in every structure, so we can't get around that. So if you really think about it, this is our worst case scenario. This is our minor resonance structure here, the minor, contributor to the overall hybrid, because it has a double negative charge on an atom that isn't electronegative, and our major contributor is over here because we've put the negative charge on the atom that is best suited to kind of harbor it, to have it on it itself. Okay, that was a very long problem number 1. Promise the ones beyond are a little bit shorter, a little bit quicker. Okay, cool. And just to state this video, once it's over and done, I'll make sure to download it. I'm gonna edit out all the parts of me doing very boring stuff like erasing the board, writing on the board, make it a little bit snappier so that if you want to review it, it's gonna be a lot shorter and better for that. Okay, all right, so for this second question, we have kind of a multiple choice. So we have here is, actually, I'm sorry, I'm gonna use more of the board. Put this way up here. We'll go. You got this. We have this. We have this. And we have this. Okay. Now, the question here is, which structure has an sp3 hybridized nitrogen? And the goal here would be picking either structure A, structure B, structure D, C, or structure D. Now, when you look at this, right, so this at its core is a hybridization question, right? We need to figure out, of all of these four structures, right, we do see a nitrogen in each, and we need to identify which one is sp3 hybridized. Now, remember, you don't have to necessarily go hardcore into hybridization theory to identify an atom's hybridization. The way I like to do it is to count, how many bonds and lone pairs, and then kind of use our orbital bank of S, P, P, and P. And for this, right, for this being sp3 hybridized, we're gonna hope to identify, a combination of bonds and lone pairs that makes up 4, because we'll need 4 orbitals to make hybrid orbitals. That'll give us an sp3 hybridization. The slight trick here is, well, let's at least rule out the ones that are obviously not sp3 hybridized. If we take a look at this structure right here, C, I hope what you're seeing is we have one bonding area, a second bonding area. Yes, even though it's a double bond, it counts as one area, and a third. So this nitrogen is actually sp2 hybridized. So this is, we can automatically kind of X that out. Now, the slight challenge with the rest of these is that, in A and D, we would see, oh, we have one bonding area, a second bonding area, a third, a fourth. We have 1, 2, 3, 4 here as well. And with this crazy little, cyclic structure, we have 1, 2, 3, and 4. So how do we decide? Well, the thing is, 2 of these structures are actually masquerading as sp2 nitrogens. The reason being is that there's resonance present. So if we take a look at this structure A, what we can really do to actually prove that this, or disprove that this is sp3 hybridized, is that because this nitrogen has a lone pair and is next door to this carbon that's double bonded to oxygen, this resonance move is valid. Because that resonance move is valid, this nitrogen is actually not a pure sp3 hybridized nitrogen. It's somewhere between sp3 and sp2, and you'll learn more about that type of concept later. But the idea is, because it cannot look like sp3, for our purposes, you can X it off. Now over here, it's the same exact thing. What you can actually see, and there's actually more going on here, but you'll learn more about that in the beginning of OChem 2, is again, there is the ability in this structure for this double bond to swing over, or I'm sorry, not that, this electron pair to swing down, and this to kick up. So again, there's resonance there in the resulting resonance structure that you have. You would have an sp2 hybridized nitrogen because 1, 2, 3. So we can see that B has no ability to draw resonance. It is stuck with its 4 bonding areas, and it can never look different than that. So that's the long way of saying B is the structure you're looking for in terms of identifying that sp3 hybridized nitrogen. All right. And we are moving right along. Cool. So now we've done a little bit of Lewis dot, resonance, formal charge, hybridization. Let's move on to the world of acid base. So let's say this is the problem. If you're wondering, in terms of numbering, I have 8 problems in store for us today. So this problem is going to say rank from 1 to 3. Rank the structures from 1 to 3 in terms of increasing basicity. Cool. And we have 3 structures below that look like this. Okay. Cool. So again, we have these 3 structures, and our goal here is to rank from 1 to 3 in terms of increasing basicity. So what that means is, and again, sometimes these problems are the most confusing because of what they ask for you and the language of how they ask it, right? So if you ever get, a bit miffed or a bit, your brain's swirling a little bit because they didn't ask in terms of acids, because I always think in terms of acids. Never freak out. Just take a deep breath. And if you need to kind of try to translate it from base to acid, go ahead and do that. But the first thing we can at least do is say, the thing we'll assign number 1 to is going to be our weakest base. 3, I'm just going to put these in boxes. 3 will be our strongest base. Now, we've dissected that at least in terms of the ranking system, but it might also be helpful to remember what the hell is a base, right? A base in terms of Bronsted-Lowry, we can just assume this is Bronsted-Lowry. That means we're looking for, we're trying to rank these in terms of things being H+ acceptors. And things that are H+ acceptors are negative, okay? So I know I'm running all over the board, but in my mind, when I think of really strong bases, I'm thinking of very reactive, negative things, okay? So in taking a look at this, one thing that will help us a bit is that, remember that weak bases come from strong acids and strong bases come from weak acids, okay? So our weakest base will be our strongest acid. So one thing we can also do is let's just draw the conjugate acids here. Just to have them. They might help us, they might not, but I have a feeling they're going to. Let's write this over here, negative. So when you're trying to figure this out, one thing about bases is that the stronger a base, you will only have the negative charge in one location, on one atom. If that charge is spread amongst the network of atoms, like a network, it's not going to be that strong because no one atom is super negative, which means it won't be that good at going out and grabbing H+. So if we take a look at these, I don't see any resonance up as a possibility here or here, but if you notice here with the conjugate base of acetic acid, I can do something like this. The minute I see resonance in a base, that signals to me this base is stable. In an acid-base world, stable equals weak. This oxygen is actually not negative. It is sharing this negative charge with this oxygen up top. So this base right here, super relaxed, super chill, does not really care to grab H+ if it's around, in comparison to these 2 structures over here that can't, they can't exhibit resonance. So in terms of the weakest base we have here, I'm just going to erase these for a second. This is going to be our number 1. I'll draw these up top over here. Okay, cool. Hopefully that explanation made sense. Now that we've identified the weakest one, we only have 2 more to go, and we need, one thing we can do here is figure out the relationship between these two atoms, because we see these two atoms have the negative charge. So if we can kind of find a relationship between them, that'll help us kind of identify maybe if one's more stable or unstable than the other. Hopefully the only thing that's really interesting is this is a sulfur and this is an oxygen. Hopefully you'll be allowed a periodic table on your first test. These two atoms are in the same family, the same column in their, on the periodic table. Remember that we have these factors when it comes to acid-base stability. We have size, we have electronegativity, we have resonance. I should have maybe arguably listed this sooner. Resonance, hybridization, oh gosh, get the point, and inductive effect. Resonance helped us out in the first one, but in the second one, this is a size problem. And remember, charges are more comfortable, charges are more stable on the larger an atom is. Sulfur is bigger than oxygen. This negative charge is happier, more stable here than it is here. So as a result, this base is stronger than this one. So we'll give this base ranking of number 2. And then this is our strongest base right there. Cool. Hopefully that made sense to everybody. So we got 1, 2, 3. 2, 1, 3 rather. Okay. Moving right along. And again, sorry if I'm kind of erasing this quickly. Just want to make sure. I always have a tendency to talk way too much, and my goal is to have this video up later tonight or tomorrow for you all to kind of go back to and review. Okay. Now this is kind of more acid-base world, so let's look at 3B, if you will. Not that that matters all that much. All right, so I'm going to throw a structure up here. Okay, so this problem, which this could probably be a little bit kinder to you on an actual exam, but I took this straight from a textbook. So the problem here is identify the most acidic H in the structure. Acidic hydrogen, acidic proton. You'll probably actually hear this written as proton, not hydrogen. Okay, cool. So most of the time when you get this type of problem, some hydrogens are kind of highlighted for you, and it's more of like a multiple choice. But we're just going to look at this, and because we're smart Joe chemists, we're going to be able to figure out exactly where this most acidic hydrogen is hiding out. Cool. All right, so remember, since we're looking for the most acidic proton here, some things that might help us out. Again, I'm going to throw these up here, and of course I could have kept them up here. Size, electronegativity, resonance, hybridization, and inductive effect. These are kind of our, some of our 5 qualitative ways we can see if something is more acidic as opposed to something else. So if we take a look up here, there's really only, in terms of like electronegativity and size, right? You usually get different types of atoms with these two. We only really have an oxygen. So these two aren't really going to help us here. We don't really have any type of like chlorine or fluorine or any super electronegative atom. So inductive effect's not going to help us out here either. The 2 things I'm thinking of are either resonance or hybridization. And just as a tip, if you can get a lot of resonance once you kind of drop off a proton and have a lone pair take its place, resonance is like really, really, really amazing because one atom doesn't bear the burden of that negative charge that results. A network of atoms do, right? You're not carrying a couch by yourself. You're carrying a couch with a whole buttload of friends, right? So I'm thinking no to hybridization, but let's take a look now. If you can see, the kind of areas I'm thinking of are this one right here, this one right here, this one right here, and this one right here. The reason why I circled all of those locations is because if we were to imagine a hydrogen, you know, a proton being taken off, right? Let's just imagine I have a base. Literally just any base. I drew an imaginary lone pair. If the base takes the proton off, it'll leave a lone pair behind. And just to save some space and time redrawing stuff, that would look like this. Lone pair and a negative charge on carbon. The reason why I'm interested in all of these locations is because they're next door to double bonds. So if I have this lone pair right here, what I can do is I can swing this down and then I can kick this up. So you can see that a resonance structure would look something like this. And hopefully I can draw this really fast. Something along the lines of this, okay? So that's why I thought, oh, okay, right here I get a resonance structure. If I get one right here, I could do a resonance structure there. If I got one here, I could do over there. But hopefully what you're seeing, and I did it last for the big reveal, if we put a lone pair right here, yes, we can swing electrons down. I'll use blue for this. We can swing electrons down. I'd have to do something with this double bond, which means I can kick it up like this. And if I redraw this structure, which of course I should have left, I have a new double bond here, and I have a lone pair right here. But the only difference between all of these positions and this position is that when you take a proton off at this position, you can actually do the resonance one extra time. So these positions yield one resonance structure, but this position yields two. And because of that, it's this position right here. What I would do is I would actually draw the hydrogen. Here, I'll cheat a little bit. If I was going to answer this problem, I would draw this hydrogen. I'd either circle it or asterisk it and just say like yields two resonance structures. As a result, is the most acidic, right? Because again, the whole idea is if this proton is to fall off and a lone pair exists there, right? A charge exists, which is naturally an unstable thing. Well, it's not so unstable, compared to these other positions, because this whole network of atoms right here are sharing them, that negative charge together. So this hydrogen has 1, 2, 3, this carbon has 1, 2, 3, 4, 5 friends carrying the couch versus 1, 2, 3 friends sharing the couch. Cool. Okay. Oh, and of course, this is the last part to C, 3. Got 3C. Let's do an acid-base equilibrium question. These were my least favorite, and I was so terrible at them when I started OChem. Okay, so the first part of this, so part, I, is predict the other side of the equation. So if we're taking a look at this right here, I did somewhat of a tricky / mean thing in that, if we take a look at this right here, if I look at this nitrogen, I can see that it in fact does have a formal charge of 0. Nitrogen comes in with 5 valence electrons. I can see this nitrogen is in control of 1, 2, 3, 4, 5 electrons. Cool. And I know you guys are very smart, and I'm probably just belaboring the point, but over here in this ethanol, this ethyl structure, we have an oxygen and a sodium, right? So we know sodium makes +1 charges, which means this oxygen actually has 3 lone pairs and a -1 formal charge, okay? So again, we're using Bronsted-Lowry acid-base definitions. We have something that is an H+ donator and an H+ acceptor. The way I was able to deduce that is that H+ acceptors, right, they like H+. If something likes a proton, it is going to be negative, right? So this is the negative part of the equation. It's neutral, but it will be the source of H+. So this is going to be our base, and this will be our acid. If I want to show the arrows, I could show the oxygen coming over here, grabbing a proton, and then because the oxygen only wants H+, these two electrons, we have to illustrate those getting dumped onto nitrogen. So I used a double-headed arrow to say oxygen's bringing its own 2 electrons to hydrogen, forming the proton, forming the bond, and these 2 electrons are all nitrogens after the fact. So moving over here, what I now know is I still have this structure, these 2 carbons like this. This nitrogen only has 1 hydrogen, and the nitrogen has 2 lone pairs now. Knowing nitrogen, what that means is it's in control of 1, 2, 3, 4, 5, 6. 5 minus 6, it has a negative formal charge, -1, and the oxygen is going to be neutral because it looks like this. And just to explicitly draw it, the oxygen has a single bond to hydrogen. That oxygen, you can bet you a nickel, it comes in with 6, it's in control of 6. 6 minus 6 is a nice flat 0. Cool. So we've done the predict the other side of the equilibrium, but maybe the more annoying part is, which side of the equilibrium is favored. Because remember, this isn't with this acid-base problem, it's not like we just plop things down and it goes to one side, to the right or to the left of the chemical equation. These double-headed arrows means it's a constant back and forth. However, one side's going to be bigger than the other, okay? Now remember, if you've ever heard this, acid-base equilibria, the different equilibriums, they drive to the weak. Why do they drive to the weak? Well, nature likes stability, right? Nature's always trying to find its way to give off energy, to go to a lower energy state. In terms of acid-base world, that means nature always wants to go to the more stable side, aka the weaker side. So if we take a look here, the way I like to do this is I look at the conjugate bases. I'm looking at these 2 right here. The way I can figure out which base is more stable is which atom is more comfortable with that negative charge. And remember, that's when you can bring back your size, electronegativity, yada, yada, yada. Hybridization, inductive effect, resonance. We see that the 2 atoms here harboring the negative charge are nitrogen and oxygen. And what's their relationship? Well, they're in the same row of the periodic table. So when it's in the same column, it's a size thing. Bigger atom is better at handling the negative charge. But when it's a row thing, remember, it's electronegativity. The more electronegative atom is better at handling the negative charge. And between oxygen and nitrogen, oxygen is better at handling the negative charge. So what you can do is, I always like to either circle the arrow like this, or if you have the luxury of just erasing everything, I like to make this arrow bigger and this one smaller to show that this direction going from here to here is a more favored, the rate of reaction is bigger going this way. All right, cool. And I think, and then we have a final part of this problem, part 3. And we need to identify the most unstable acid. Okay. I kind of like this wording because, again, it's really just a fancier way of dressing up asking what's the strongest acid or what's the weakest base. Most unstable acid, right, is another way of saying strongest acid. Because if I asked you the most stable acid, that's another way of asking what's the weakest acid. So most unstable means strongest. So remember, this is our side favorite equilibrium, and acid-base problems, equilibria, they drive to the weak. They drive to the more stable side. So if this is the weak side, the stable side, this is the strong side. So now that we know what the strong side is, we can figure out just which one's the acid. And what that means is this is the base because it's the negative one. So this is our H plus acceptor, and this is our H plus donor, and that is our most unstable acid. Okay, I know that was a lot of vocab and a lot of talking, and I promise, actually let me double check that. That is the end of our acid-base stuff for today. Cool, for this review. Acid-base unfortunately never goes away. Okay. All right. Let me just check the time really quickly to see how we're doing. Okay, we'll keep it going. All right, a little bit more of a problem that isn't super duper, I don't know, annoying in my opinion, a little bit more chill, relaxed. We're just gonna name this structure using IUPAC systematic naming. Okay. Let me just make sure I drew this correctly, because if I didn't, that will make this whole experience awful. Okay, cool, think so. All right, so if we take a look at this structure, remember our first, so the one thing to note is there's nothing, super crazy going on in terms of different groups and things like that. What I usually find, and again, this could maybe just be my experience at, with seeing exams from the University of Pittsburgh and stuff, these naming problems on exams are usually pretty simple, but they usually hone in on, can you identify the parent chain when things are, there's chain length ties and branching at different positions. So when we look at this, remember our first priority is we need to find the parent chain. And that means we need to find the longest parent chain. And if we have a tie, then we go from there and we use branching to kind of break the tie. So my advice to y'all is count, count, count. Just take your time, go through as many paths as you can, because I used to always just go super quick and I picked the wrong parent chain way too many times. 1, 2, 3, 4, 5, 6. Okay, so 6 could be our longest. 1, 2, 3, 4, 5, 6, 7. Okay. Nope, we're looking for 7 length. 1, 2, 3, 4, 5, 6, 7. Okay, so we have a couple 7s. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Okay, that's another one. Actually, not really, because these branches are kind of the same. Okay, so it looks like 7's our longest. And what I'm gonna do here is I'll do this one in blue. And then we had 1, 2, let me do that in black actually. 1, 2, 3, 4, 5, 6, 7. What I'm actually gonna do is reverse this actually, and I'll explain why in a second. 1, 2, 3, 4, 5, and I can't count. 4, 5, 6, and 7. Okay, so we have a chain of 7 and a chain of 7. With ties in terms of length, we use branching and figuring out lowest, difference of lowest position and quantity at those positions in terms of branching to break ties. So you can see at 2, we have one single branch. One single branch. We actually converge at 3 and 4. And I hope what you see is, obviously we didn't, no tie was broken at 2. We were on the same carbons for 3 and 4, but it's at 5 that we see the point of difference. At blue 5, we have one branch, but at one methyl group, one extra substituent. But at black 5, we actually have 2 substituents. So that is why the point of difference here is at blue 5, black 5, and it's the 2 substituents here that beats out the 1 substituent. So we're no longer even considering the blue. And that's why the black chain right here is the one we will go with, okay? So we've identified the parent chain. we found the longest, and then we even used branching to break the tie. And now what we do from here is just, you know, almost like the plug and chug. We go through our structure, we name our substituents, and then we'll alphabetize them and put the whole thing together. So before I even get started, we have a chain of 7. Our parent chain will be heptane. I know it's annoying, but put in the time to memorize, you know, whatever your professor told you, 1 to 20, 1 to 15, whatever it might be, just have those locked and loaded upstairs. Okay. You know, I like to just go through numerically. So at 2, we have a methyl. What I like to do is when I run into a group, I scan the rest of the structure to see, does that group come up another time? So at 2, we have a methyl. I don't have that at 3. I don't have it at 4, but I actually have it 2 times at 5. So for here, for the first group, we have 2, comma 5, comma 5. Numbers are separated by commas, but then when you go from number to word or word to number, you do a dash. We have 3 methyls, so I'll do tri-methyl. Cool. Now at 3, and again, hopefully you have your common naming under control as well, because it really helps in these scenarios. This kind of looks like your pitchfork situation here, and this is an isopropyl group. So at 3, and again, if it helps to draw a little squiggly like that, we have 1, 2, 3 carbons, so you know it's going to be a propyl of some kind. And since we're attached to the middle, that's why it's an isopropyl. So we have 3 isopropyl. Okay. Now here's where the common naming will really help you out. We only have 1 more substituent in this molecule, and it's at position number 4. For 4, we have this kind of monster over here. But it's not really a monster. There's 1, 2, 3, 4 carbons here, okay? The way it's drawn kind of looks funky, but I promise you, if you had something like this, 1, 2, 3, 4, you would call this whatever, butyl. Now remember, we have extra, you know, common names for different types of 4 carbon chains. And if you can believe this here, if I actually kind of redrew this like this looks a lot like this. And if I drew something like this, you would tell me this is sec-butyl bromide. So at 4 right here, we actually have, and people write this differently. I might not be up to date with the times, but I've always done 4, you know, the number hyphen sec hyphen butyl. Sometimes you see parentheses like this. Just do whatever, you know to be what it is. As long as you call it sec-butyl, that's the most important part to me, at least. And I'm sure to your teacher as well. Cool. We actually have all the substituents named, and we have the parent chain. So now we just have to stitch this together. Before I do that, I like to alphabetize my substituents. Because remember, there's a little bit of quirky rules there. Stuff like di, tri, tetra, penta, those do not count, right? But things like iso, cyclo, neo, those do count. And sec and tert do not count. So I like to underline the letter that will count. In here, it's going to be the M because the tri doesn't count. Here will be the I because the I does count. And then for 4, we ignore sec, the S in sec, we go straight for butyl. So in terms of numbering, this comes first, this comes second, and that comes third. So putting it all together, you'd get 4 sec, butyl, 3 isopropyl, 2, 5, 5 trimethyl, and then remember, this is important. You go from last substituent, this final letter runs straight into the name of the parent. No space, heptane. So the naming questions, unless your teacher is a hardcore naming person, just make sure you have the process down because they are nice and easy points to snatch up. But easy, meticulous type of problem to make mistakes. Like I'm not saying it's a cakewalk. You got to make sure, if you have the process down, lower chance of having those little errors, happen. Okay, cool. let's move on to problem 5. Okay. What we have here is, okay, so we have two things we need to do. We have to draw the mechanism for the reaction below. Okay, so we have to do, this problem will look like this. This is going to be free radical chlorination. So this is that's my very pathetic attempt to write H nu for light. Light. Okay. So we have the reaction given like that. And in terms of the mechanism, all we really need to show is the steps of propagation 1 and propagation 2. And what that means is, like, you wouldn't have to show the initiation step. So there's a second part to this, but let's do the mechanism first. I'll go ahead and show you initiation. Initiation is just that part where you have 2 chlorine molecules and the light energy is enough to actually split this bond in a fashion where one atom gets 1 electron, so we use single-headed arrows, and the other atom gets the other electron because each bond is 2 electrons shared. Remember, vocab alert, homolytic cleavage, because it cleaves the same way. It cleaves in like the, equal way. So you get 2 Cl atoms that are radicals. Radicals because you have an unpaired electron. You wouldn't have to show this, but now we'll move on to propagation 1, which I'll call P1. This is the, P1 and P2 are the juicy steps that give you your haloalkane, your alkane with that halogen on it. So in P1, what you have is you have to expose a CH bond, and then you have this chlorine come in, and the chlorine radical wants to bond with this hydrogen. So for this hydrogen and the chlorine to get together, each one needs to come together with 1 electron. So this is hydrogen saying to carbon, hey, we had a great run. You've been great to bond with, but I'm leaving. I'm packing up my 1 electron and I'm bringing it together to chlorine to form a new bond, an HCl bond. Carbon's obviously devastated, super bummed, but the one thing you do need to show is you need to show the movement of both electrons in this bond. So you've shown where hydrogen's going with its electron, but you need to show carbon getting its 1 electron. So it basically becomes the radical. So after this, you have HCl plus a carbon radical. So you can just expose 1 lone electron. That's P1. For P2, you show this carbon coming back. It's determined. It's not going to be a radical for much longer. You have a ton of chlorine gas around, okay? So it's actually the first thing it'll bump into is another chlorine Cl2 molecule, most likely. This carbon says, you know what? I'm going to bond with a chlorine. So with this bond right here between the 2 chlorines, you'll show this chlorine on the left taking its 1 electron in the bond, buddying up with the carbon, and then you'll show this chlorine over here becoming a radical. So that's how you get the ethyl chloride. And then the beauty of this reaction is that it's a chain reaction. Initiation really only has to happen 1 time to make 1 radical, because propagation 2 actually produces the very thing initiation makes to get this thing started in the first place. But anyways, that's the mechanism. So in terms of kind of drawing the mechanism, that's what we need to do here. Now, what I'm going to do is I'm actually going to erase this top part, and we'll do the second part of this problem. And I really, really, really enjoy or like this second part of the problem. So what we need to do here is we need to draw an energy diagram for, that shows P1 and P2. And some given information here that we're going to label as well. I'm just not writing it here, but the heat of reaction for P1 is plus 2 kcals per mole. I'm just kind of making these up. Delta H P2, they're kind of accurate numbers, but don't worry about them so much, is negative 27 kcals per mole. So, and the one thing we need to do here, and again, I'm not writing this down. Actually, maybe I will. So, things we need to do. Label delta H P1, delta H P2, and delta H of the overall reaction. And then one other thing we need to do is respect Hammond's postulate. Now, the idea of Hammond's postulate is if you have endothermic reactions, you have a late transition state, and with exothermic reactions, you have an early transition state. Now, why do we care about that? It's actually going to make our energy diagram look more accurate. So if I just do energy, or actually what we could probably say instead of E is just, we could just put, well, we could just put enthalpy, whatever, energy, H, whatever you want to put up there. We know that P1 is actually endothermic. Because endothermic reactions are slow, you go from lower energy to higher energy. It takes a little bit of time for the reaction to actually kind of click. You're kind of chugging along, and then all of a sudden towards the end, it kind of just gets over the hump. That's why Hammond's postulate says you have a late transition state. So what I'll do for this first one is you can pick anywhere from where you're starting. And what I know for sure is I'm going to end up higher than where I started. Okay, endothermic means you gain energy, increase in energy. Now, I need to be very careful about my hump. Every energy hump is either going to look like this or like this. But because I have a late transition state, I want my hump to be closer to the products because it's late. So you kind of draw something like this, if that makes sense. Because this is the transition state, the peak. Okay? And if I even want to get ahead of myself, I know from where I end to where I start, this is my delta H P1. This is the plus 2 kcals per mole. Okay? Now, if we look at, that represents this step right here. To get this second step down here, I need to, we know the delta H here is negative 27 kcals per mole. This is exothermic, and it's much more, it's a lot more exothermic than the first step was endothermic, right? We're almost, it's 25 kcals more. Because this is exothermic reactions fast. You kind of go right away. Instead of having a late transition state with endothermic reactions, you're going to have an early transition state with an exothermic reaction. So I know I'm going to end lower, so I'm going to go lower. So what I'm going to do is I'm going to kind of do my peak first, and then I end low. So as opposed to this being late relative to where we start, this is very nearby relative to where we start. And what I know for sure is from end to beginning, this distance right here is my delta H P2. So this is the negative 27 kcals per mole. So we've respected Hammond's postulate. This part's done. We've labeled delta H P1 and delta H P2. The last thing we need to actually label is delta H reaction. Now, delta H reaction, enthalpy only cares about from where you ended and where you began. So it doesn't even matter what happened in between here. From where final minus initial. Final minus initial. So if you take a look here, we can actually get that distance by saying that, oh, okay, we can do 2 minus a negative 27. Or if you just, you can add the enthalpies here. Maybe that's just an easier way of explaining it. If we add the negative 2, right, we gained 2, but then we lost 27. Overall, that means we gave off negative 25 kcals per mole. And that is delta H reaction. I really like problems where you have to do a direct concept and then take it to an energy diagram, because that really, in my mind, tests if you understand something. And trust me, I have messed up an energy diagram or two or a 9 or a 20 in my day. So I really like this problem, especially because this is kind of the unit where you mostly talk about Hammond's postulate. And yeah, I guess I enjoyed the problem. I'm nerding out. Cool. Let's keep it going. We've got 3 more. And just to say, you would never have to come up with those energy values. Someone would need to explicitly tell you, hey, this is going to be an endothermic step or an exothermic step. So don't worry about where those +2 and negative 27 kcals per mole came from. That would have been given information. All right. Let's take it to cycloalkanes. So for problem number 6, let's say we have 2 structures that look like this. We have one like this, cyclohexane with 3 ethyl groups. If you're not familiar with this notation, it really just looks like this. It's a wedge where this is 1 carbon, and then this is a second carbon, but it's very, very, very common, and you will see this in your organic career, to instead abbreviate that as ET, okay? And then we have something that looks like this. Ethyl as a wedge on top, but on the other 2 positions, we have dashes like that. Okay, cool. So these are 2 different structures. The problem we have at hand here is identify the more stable cycloalkane. Okay, so, or the more stable structure, right? Someone could be very vague with how they're wording this, but what the point of this question is identify the more stable structure between these 2. Now, if anyone's ever asking you that in the context of cyclohexane structures, just know what they are asking you is a chair question. You can't just look at this and know right away which one's more stable than the other. However, knowing how to draw the chairs and knowing how to kind of identify, oh, this structure has a limited amount of steric hindrance, strain and whatnot, that's how you're going to identify this. So really what we need to do is draw both versions of the chair here, both versions of the chair here, because remember, you can draw one version, but we can flip back and forth. And we can basically, since all these groups are of the same size, we can basically identify the given chair conformation that has the most equatorial groups. Because when groups are equatorial, strain is minimized. So what I'll go ahead and do is draw a chair like that. And again, if you're having trouble drawing chairs, I always like to draw an upside down propane, go to the middle, trace down a little bit, draw another upside down propane, connect the dots. It'll get you to draw a very consistent chair every time. Okay, so these, I'm gonna go ahead and number these. 1, 2, 3, 4, 5, 6. Now I'll do that over here. 1, 2, 3, 4, 5, and 6. Now remember, I'm gonna draw this ethyl group on 1. This, remember, on your cyclohexane chairs, you go from peaks, where a peak is 2, when you trace from the carbons that are sandwiched, if you trace from the adjacent carbons, if you're going up to that carbon, it's a peak. And conversely, if you're going down to a carbon like this, it's a valley. So at a peak carbon, like we have at carbon number 1, you have up axial, down equatorial, slightly down equatorial. So since we have a wedge on position 1 and wedges on flat paper basically represent something coming out at your face, this is up axial. Wedges are up, dashes are down. So I can erase this. Now if I go to 2, 3, 3 is also axial, up axial here. 4, 5, 4, 5, and 5 is also a peak here. So we are up axial because these are all wedges. Since these are all peaks, we're all up axial. I'm gonna go ahead and draw the flipped chair just to stick with one thing at a time, because one thing we know for sure is having all these groups axial is really not okay. So this is a pretty bad structure, right? This is like worst case scenario in terms of stability. Now, when you do your chair flip, remember your leftmost carbon is still your leftmost carbon. Every peak becomes a valley and every valley becomes a peak. So your numbering stays consistent. I know people have other strategies, so if you use a kind of different mental model, please do that. Now, up is up and down is down. That never changes. At this peak or valley now, right, because we're going down to 1 from 6, down to 1 from 2, we have down axial, up equatorial at a valley position. So what you can see is, since ethyl is up here, it was up axial, now it's just up equatorial. Okay, we don't need this anymore. 2, 3, 3 is also a valley, and we can see we were up axial. Now we'll be up equatorial. Again, this is all because we're wedges, and wedges are up. And 5 is also, right, we go valley, peak, valley, peak, valley. We're also up equatorial. In these back ones, it's a little tough. You can either just draw it kind of up to the left, up to the right. That's totally fine. As long as you don't go straight up, you're good. Okay, this is looking like a pretty good structure. We're all equatorial here. So this is looking really promising. Really quickly, let's draw both of the chairs over here. I highly recommend, even though this is looking really good, because how could this beat all equatorial? Still draw the chairs. If we take a look, it's the same thing, really similar. 1, 2, 3, 4, 5, 6. We have up axial, right? Because this is a wedge is up. This is a peak. Up is axial at a peak position. Now for 3, over here, we have a dash, and a dash is down. Now we're at a peak over here. Up is axial, so down is, equatorial is slightly down like this. Again, kind of draw it like slanted. It's okay as long as you don't go straight down. Okay? And then 4, 5, we're at a peak here. So what we can do is we can go, or this is down. So at a peak, down is slightly down like this, at equatorial. Okay, so we have 2 equatorial, 1 axial. This is not better than this. All equatorial beats the fact that only 2 of these groups are equatorial and 1 are axial. But let's go ahead and do the chair flip. And if you're picking up on the patterns, you're gonna realize this chair we're about to draw is worse than the one we just drew. We have 1, 2, 3, 4, 5, and 6. What you can know is that everything that was, this is gonna be up at 1, but everything goes from axial to equatorial, and everything equatorial goes to axial. So what we'll have here is up equatorial. At 3, we'll have down axial, and at 5, we'll also have down axial. So this doesn't cut it, and this doesn't cut it in terms of being more stable than this chair. All equatorial takes the cake. So what you'd say on your exam is that this is the more stable structure because it has a chair conformation that places all of the substituents equatorial, minimizing overall strain, and therefore having a lower energy than this molecule on the right. Alrighty. We've got 2 more. Stick with me. All right. So for problem number 7, this is some information I'm going to write up on the board really quickly. I'm going to give two reactions that look like this. And the question here is, one reaction occurs and one does not. What we need to kind of figure out is which one occurs, predict its product, predict the result of the free radical bromination, and then explain why the one doesn't occur. This is also kind of a long-time favorite problem of mine. Cool. Okay. So if we look here, right, it's kind of confounding. The one thing that really jumps out, right, is that we're doing the same reaction in terms of, right, we're both doing a free radical bromination in each case, but the reactant is different, right? The molecule undergoing the reaction is different. This is propane and this is cyclopropane. So what's the difference? What I will say is that this is the reaction that does not occur. So you can put in a no reaction or it doesn't happen. And then remember, in terms of predicting the product, a free radical bromination is extremely selective. We always go to what we call the most substituted position, right? So we have two primary carbons here, and then right here we have a secondary carbon. Because this carbon is attached to two others, these are only attached to one. The bromine is really picky, selective. It goes to that central carbon right here. So that kind of like takes care of this and this. And of course, you know, I just told you, I'm sure no matter what, y'all could have come up with this for sure. When I first saw this problem, I did not know how to do it. So I know this one was like, I know this is definitely the most interesting part right here, these two, which are linked together. The reason why this doesn't occur is because it just takes too much energy. And here's what I mean by that. We know that in propagation 1, if we like took a look at both of these would have a step very similar to this. In the case of the bottom reaction, bromine comes in, whoops, and it basically facilitates the breakage of this carbon-hydrogen bond. And then you get a carbon radical, okay? Now that has to happen up, you know, in the case of cyclopropane as well. And it's right here that really explains why this doesn't work. And this is a bit tricky because it really does kind of make, this is, not that it's a footnote when you learn this stuff, but I feel like when you're learning free radical chlorination and bromination, what we're about to go into is, at least I kind of filed it away as a footnote, but it is really important. When you have a radical meaning an atom with just an unpaired electron, right here, this carbon, both of these carbons, before they undergo this change, we haven't drawn it, but there's another hydrogen in both cases, right? These carbons are sp3 hybridized, which means they are tetrahedral. They have a tetrahedral shape. They like 109.5 degree bond angles. Now, when we go into the radical, crazy enough, these things exist like this. We know there's one hydrogen left over, right? This one's left over and this one's left over. I'm kind of drawing these sideways. So the thing is, they really only have 3 bonding areas. One for this carbon, 1, 2, 3. 1, 2, 3. And weirdly enough, the radical electron resides in a p orbital all by itself, meaning that radicals are sp2 hybridized, and they like, you know, their shape is trigonal planar, and they like 120 degree bond angles. Now, this is what explains why this reaction doesn't go. Basically, by this step occurring, cyclopropane, which is already forced to be in a triangular shape, right? Cyclopropane is already forced in a situation where these bond angles, right? This is tetrahedral. 60 is far less than 109.5. There is a good deal of ring strain here. Then think about what you're asking this carbon to do. Undergo free radical bromination and basically say, hey, I know you're dealing with 60-degree bond angles, but you want 109.5, but I want you to do this thing where you're actually going to be worse off after the fact. Basically, what nature is seeing is you're trying to do something like this. Cyclopropane might exist like this, but you're asking it to go like way up top here and be like this. You're trying to do a very endothermic step. Breaking this bond requires a tremendous amount of energy to be put in, and that energy just doesn't, when you're just trying to do it, it's really hard to do. So this is much more realistic than this. And that's why the top reaction doesn't occur. It comes down to the fact that you start off tetrahedral sp3 hybridized. You need to go through an intermediate, a temporary structure that is sp2 hybridized trigonal planar, the radical that likes 120-degree bond angles. But the ring strain is just too great to overcome. You need to, like the energy required is so high that the reaction doesn't go. Okay. If that didn't make sense on the first try when this video comes out, listen to this again, because I remember this melted my brain the first time I heard it, but after hearing it a few more times, it made a lot of sense. Okay, gang, we have one more. We're gonna end with a Newman projection problem, and then we will call it a day, and you no longer, if anyone's still here, I'm not really looking at the chat, and drop off. Okay. Last but not least, the problem here is going to be draw the most unstable Newman projection conformation for, and I'm about to give you a structure name, and the structure name here is 4 bromo 2,2 dimethyl pentane. Okay, cool. All righty. So first off, let's actually draw this structure because we can't do anything until we know what it looks like. We have a parent chain of pentane, and we have 2 methyl groups on 2. So what I'll do here, oh, and I actually forgot, I should say along C3, C4 bond axis. Okay, cool. So we got methyl group, and then 4 we have a methyl or bromo right there. Cool. All right, so the problem here is saying let's draw the most unstable Newman projection along C3, C4. So what that means is let's have an eyeball take on this perspective of C3, C4. So that means the eyeball will see C as the first carbon, aka the circle carbon, or sorry, the dot carbon, and 4 as the circle carbon. What I mean by that is if we draw our standard Newman projection structure, our format, the dot is what I know to be the convention of as the first carbon, the circle is the back carbon. So this eyeball is going to see C3 first, C4 will be in behind. Cool. Now let's play the game of what's attached on C3. Let's draw C3 first. What C3 has is 2 hydrogens, right? We've drawn the bond between C3 and C4. That's the dot and the circle. C3 has 2 hydrogens. I'll draw my lines from the dot because that means that they're from C3. And then this is just a big T butyl group, a tert butyl group. So I'll go like this. Cool. Now what I can do is look at the back carbon. And I have a bromine, a methyl group, a CH3, and a hydrogen. Now I want the most unstable Newman projection. When you hear that in terms of Newman projection, you want the highest energy structure. So what we want is an eclipsed conformation, because when you draw something eclipsed, that means groups are as close as possible, possibly even bumping into each other, maximizing both torsional and steric strain, right? And we want the biggest groups aligned if possible. Well, not if possible. We want the biggest groups aligned. Now, the biggest group on the back is this bromine. And I think it's very obvious that the biggest group on the front is this highly branched T-butyl group. You'll get your biggest groups much like you kind of think of them for cyclohexane substituents. Highly branched and very big in terms of molecular weight. So when I'm drawing these lines now from the back carbon, I want to make them eclipsed, right? If I draw something over here, that means I'm doing a staggered structure. We're not doing staggered. Eclipsed is any eclipsed structure has higher energy than a staggered structure. So what I'll do is I'll kind of draw bromine like this. Kind of indicates that they're in a line, but I can't draw it like right behind. And then from there, it actually doesn't matter where you put the CH3 and the hydrogen, because the two groups in the front are just hydrogens themselves. So I could put the CH3 down here and the hydrogen here. And the fact that these two are eclipsed right here means we have the most unstable Newman projection for 4-bromo 2,2-dimethyl pentane. Okay, gang, this went a little bit longer than I thought it was going to, but if there's anybody still here, yeah, maybe there is. Oh, there's 8 people watching. You 8 people are the absolute homies. Thank you for tuning in. Like I said, I'm going to do my damnedest to get this edited and published, but if you are here, that means you're probably a little bit more tapped in than into this 27-year-old's life than most other kids taking organic chemistry. So 1, you rock. 2, I hope this website, YouTube channel is a good resource and that it's helping you. If you have any feedback, I'm just an Instagram DM or an email away, at joechem_io on Instagram, joe@joechem.io, Gmail. If you have friends, please tell them about Joechem. No matter what, you're all the best. I will be definitely doing this for next month for exam 2. If I'll be making sure to communicate that ahead of time. If you have any problems for that, make sure to start saving them away. But yeah, have a great night, everyone. And I hope to see you all in the next video.